Okay, and recording. So for my tutoring video, we're going to go through some biochemistry problems from a practice exam, as well as some mechanisms, just to get a basis for people that are in chemical engineering or taking biochemistry. So the first problem here, that's shown on the screen, is draw a chemical structure of alpha D-glucose 1,4, beta D-galactose, and then indicate any and all anomeric carbons. So, the first step here would be to draw the alpha D-glucose, which then is attached at the anomeric carbon, so then to be able to draw the beta D-galactose. So let's get right into it. Let's get onto page thing here. So, for the alpha D-glucose, the best way to draw glucose is starting with a normal chair formation. So you draw a line down here, line up, line down, up, down, up, and then you just connect it here. Kind of looks like a lightning bolt or something like that. And because it's a glucose or a sugar, you need to draw your oxygen here. And to draw glucose, everything is going to be in plane or equilateral. So if you were to draw the carbons of this, the alcohol groups, they would be all equilateral. So this OH would be planar here, pointing down. OH would be pointing up here. OH would be pointed down this way. And then your methyl into an alcohol group is pointed out and then back up. And here's your OH. So this is the basis of a glucose, but because it's a alpha D glucose, that means the connection between this and the galactose is going to be off of this pointed downwards, because that is alpha D. And galactose, basically everything is the same here. So the one connection here will be the 4 connector onto the galactose. So this will be pointed down, oxygen, and then this, and now if we're counting, so this is carbon 1, 2, 3, 4, 5, and 6. We can see that it'll connect right here on this carbon here for the galactose. So we're just going to redraw this structure here, except is connected to this alpha-meric carbon right there. So this is the base structure. And to make it galactose, that's just to draw, but the alcohol groups on it. But first, in my opinion, because the question did state indicate any and all anomeric carbons, that is the last carbon in the group. So if you're counting 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, depending on which way you go, depending on which way the ring structure folds in on itself due to Fisher projections, it will always be, at least in this view, this carbon right here. So let's just draw that a nice red color. So that part of the question is done. And let's just do a note right here. All red labels equal anomeric carbons. And because this is our glucose, and this is our galactose. Now we just have to draw the rest of these carbons here. So, sorry, alcohol groups. So there's an OH here. OH coming down here. OH here. And boom, boom. Methyl into an OH group. And note that there is a carbon right here and right here. It's just hard to draw that planar. And to see the difference between glucose and galactose, all you have to do is look at the alcohol group right here. See how this is pointed downward and planar versus this guy who would normally be pointed upwards in this group. So whenever you want to be able to draw galactose versus glucose, you could just draw everything planar for glucose, and then just know that galactose has the 3 or the 4, in this case the 4 because we're counting from the anomeric carbon. The 4 carbon will be pointed upwards. And that would give you the 6 points for this question. So let's go down to number 26 here. Draw a chemical structure for a peptide with the sequence tyrosine, glutamic acid, leucine, and tryptophan. Ooh, interesting one. Okay. File. New. Don't save. Okay. So, first, let's write out what the question is asking. So it's saying, draw peptide, tyrosine, which is, they give us the 3-letter code, which is TYR, glutamic acid, or glutamate, depending, leucine, and tryptophan. But a key part of this, right here, is that they ask you to show, obviously, stereochemistry, as well as it being in a pH of 12. This is really important because in a pH of 12, things are more likely to be protonated than not. That includes in our actual structure chain of the peptide, as well as any of the R groups that are attached to these. So let's first start off with drawing the base peptide. So because it's a pH of 12, more likely than not, because of the pKa value of an amide group, this proton, or this amide group is going to be NH3 plus at pH of 7. But because the pKa is 9, or roughly around 9 to 10, when it gets above this threshold, it's going to be deprotonated and have a value of NH2. So, to draw the tyrosine, let's first draw out this, a value of O. Oh, let's pause the recording real quick. Give me a second here. Okay, sorry about that. Okay, let's continue here. So, because it's a pH of 12, it's very important to note when we're drawing this tyrosine that this R group here is going to have very special properties. So we draw our, what would be phenylalanine, and draw that extra OH group on the end, but because it is above the pKa of what tyrosine would be protonated at, which is 10, around 10. Same thing with the amide group. Its pKa is about 9 to 10. This will be protonated. So actually, this becomes O minus. And we just keep going along with our groups here. So this would be like this, double bond, oxygen, nitrogen, and let's just draw the rest of the backbone first. Make it easy on ourselves here. So this is 1, 2, 2, 3, and let's draw one more. Oh, sorry. One more. Boom, boom, and then an O minus at the end because we're at, normally it would be an O minus, unless the pKa was very low, or sorry, the pH was very low. So, this is our peptide backbone. And you see how I drew the wedge here? Because this rotation should always be an L conformation, this needs to be a dash to go away to complete that L versus D conformation. Because everything in the body, barred very special chemicals, are always going to have this rotation of the bond of this alpha carbon. So, did tyrosine. So glutamic acid. So glutamic acid and aspartic acid are very similar, except they're different in one carbon. So glutamic acid has 1, 2, 3 carbons, and on this third carbon is your carboxylic acid. And usually this carboxylic acid is going to be protonated as well, because the pKa of glutamic acid or glutamate is roughly 2 to 3, maybe a little higher, but it's within the ballpark of 3. And again, because the pH is higher than the pKa of this glutamic acid, this will be protonated here and not have a proton attached to this free oxygen. So for the next part, sorry about that interruption again. But to continue with leucine, so leucine only has only has carbon groups attached. But similarly to how this nitrogen is attached to this carbon here, because it's down in the planar formation, that means the hydrogen is back here, meaning that the methyl group here has to be in wedge and not dash formation. And leucine is very similar to valine, except it just has an ethyl with then the splitting off of the two methyls. But I'll draw it like this, just to spare confusion, so it doesn't look like one straight line. So you'll have a methyl group, wedge here, and then a methyl group coming off of the wedge with 2 methyl groups attached to it. Or if you like to think of it as an ethyl group, so an ethyl group and the wedge formation, and then 2 methyl groups attached to that. Okay, and that's good for leucine. Tryptophan. So tryptophan is the last one here, and it's a very funky looking molecule. So it is a 5-carbon ring and a 6-carbon ring. However, in the 5-carbon ring, I misspoke, sorry. It is not a 5-carbon ring. It is shaped like a 5-carbon ring. However, it would have a nitrogen at the head of the cyclization here. And then it shares a double bond here with the hexane here, or benzene, I should say. So this would normally has a pKa that cannot be protonated. So this N here has an NH that cannot have this proton be taken off. And then at the very end, again, just to say that this is protonated because of the pKa value of a carboxylic acid is very low, 2 to 3. And good practice here is, well, let's do it actually. What if the pH value was not 12, but instead 2? What would that change? So let's go back through here. Let's give us a little bit more room without the check marks. And what would change about this if our pH changed? Well, let's go from left to right. This amide group has a pKa of around, 9 to 10. Now that we are below that value, things would tend to want to be have more protons on it. So this NH2 would then turn into NH3. And similarly, because this pKa value of the tyrosine is roughly 10, this would also likely be protonated in solution. So you would just get rid of this negative sign here and say, hey, that's going to be an alcohol group that has this proton on it. And I guess you can see the pattern here. If we just kind of go down the line, this carboxylic acid, if we're saying even if its pKa is roughly about 3, maybe a little bit higher towards the 4, but it's around 3 to 4, it's going to drop its negative sign here, and that oxygen is going to want to grab a proton. The leucine, because of its polarity here, its non-polarity, because it doesn't have any polar groups on it, just because it's a bunch of carbons, stays the exact same. So these three are good. And tryptophan, like I just said before, because of the nature of this nitrogen with the benzene attached to it, doesn't really want to give up this hydrogen anyways, and it can't really be protonated that well. So the tryptophan would be the exact same. And don't forget, the last thing is this carboxylic acid following the backbone right here. This guy would want to be, and it's NH3+. Sorry. This guy would want to be protonated here because similarly to glutamic acid, it has a pKa of roughly 3 to 4 within that range, so then that oxygen would want to be protonated. So those would be your two answers if the pKa changed. Just note that for these type of problems where it's drawing out the peptide formations, even if you can't remember the specifics, like, oh, you forgot that tyrosine has this group, but you knew it has some sort of structure like this, just try to draw as much as you can and to get practice with memorizing the different amino acids. But if not, there's always very close things. So tyrosine is very close to phenylalanine, glutamate or glutamic acid are very similar to aspartate and aspartic acid. Glutamate and glutamic acid are the same thing, but glutamate is very similar to aspartate. Leucine is very similar to valine and isoleucine, just difference in rearranging the methyl groups or ethyl group. And tryptophan is just one of the weird ones that just have this very unique structure. Okay, let's move on to the next problem here. So arginine can distinguish. So here's another amino acid we're going to have to draw. So let's bring it up right here. So we're going to have to draw arginine, which has the 3 letter symbol of ARG, can distinguish between guanine and adenine by forming 2 hydrogen bonds with guanine where only one is possible with adenine. Adenine. So we're drawing a GC base pair. So let's write that out. That we are drawing a. So first we're going to draw GC base pair. And we're going to include both riboses, so both the guanine and the adenine, and then the side chain of arginine to show how it can do two hydrogen bonds with the guanine in the specific carbons, so the C6 and the N7, and then just saying is if this is a major or minor group interaction. Okay, so this is a real interesting problem, because even though it seems like it has a lot of parts, it's really just asking us to draw how. It's really just asking us to draw the connection between arginine and guanine, and then arginine and adenine to see, hey, how are these going to react with each other? So let's get on that. If we were to draw, let's start with the arginine, just to be easy. So we don't know what peptide it's coming off of, but we're just going to assume that the R group here is pointed the way we want it to be. So we're going to have that dash pointed downwards for us. But as you could, if you go back previous in the video, you can just see that I flipped the amide group from to the right side, so that's okay that this dash is pointed downward here. It's the same as if I swapped where these two, where the carboxylic acid group is with the amide. But for our sake, this would be easier. So arginine is very complex because it has a methyl that has a lot of moving components to this. So it has 1, 2, 3. Let's move it back in to do 4. And then it has similar structure to what carboxylic acid is. However, instead of it being oxygens, they are nitrogen groups. So here are the two nitrogen groups. And then let's show the base pair of the guanine interacting with this arginine. So in the question it says add the side chain of arginine to show how it can form two hydrogen bonds with guanine by bonding the carbonyl oxygen on C6 and C7 of the nitrogen. So if we are drawing guanine here, let's give ourselves a little bit more room to draw this. Guanine has oxygens attached on the bottom. Well, actually, let's start a little bit more simple here. Let's show the hydrogen groups here off of the arginine, and then the interaction with the R group of the guanine. So guanine, similar to tryptophan, has a pretty weird R group. It has a nitrogen group here that kind of has an attraction here. Oh, let's draw that double bond a little bit better. There we go. And even though it looks a little funky, let me draw this side a little bit better here, because this is supposed to be a double nitrogen here, and then this is a double bond. There you go. And it is worth to memorize. I'm trying to remember off the top of my brain if this is, yes, this is correct. Let's draw that a little bit smaller just to be able to fit. Okay, there we go. And then this is a double bond oxygen. And this has an H group. And this is a methyl group coming out. And I'm really drawing out each of these hydrogen bonds onto these nitrogens just to really kind of show the attraction here. So usually in nomenclature of like an amide group, so a nitrogen group, you just write NH2 or NH3 plus. However, in an image like this, so if they kind of ask you this question, it's okay if instead of writing it like this, you kind of draw out that hydrogen bond to kind of show that proton interaction with the groups. And just because it's a lot easier to both draw and oh, it's both easier to draw and kind of show what the question is asking. But if they ever give you a question on guanine, memorizing the structure of it is very important because usually they do not give it to you on a test like this, and it is based off of memorization. And it's very important to note that the difference between guanine and adenine, which I'll draw in a second, is just this secondary, what is that, 1, 2, 3, 4, technically a 5-carbon ring structure-ish, and not just a hexane group. So let's draw the interactions here with adenine. So adenine is very similar into which it has the same kind of R groups of the oxygens coming off of here and here. Let's do that and that. There. So it's just mirrored, and then it has a nitrogen group coming up, and it's just a benzene ring with nitrogens replacing some of those carbons at the 1,3 or the 4,6 or however you want to think of it. And I could have drew this a little bit better, but one of these oxygens should be, this oxygen should be attracted to one of these hydrogens on the guanine. This nitrogen group is attracted to this hydrogen here, and then there's a nitrogen group coming off of here that I'm going to stretch it real far, but in plane these bonds stretch and come back all the time. This oxygen is attracted to this guy here. So normally this connection of the GC is how this is how adenine and guanine are attracted to each other, is because of this oxygen, nitrogen, hydrogen attraction uh, due to intermolecular forces and just close proximity. And the amino acid here is attracted due to similar properties. The hydrogens off of those, I guess you can't call it carboxylic acid, but the carboxylic-like structure with free protons have the attraction from both the nitrogen and the oxygen group and the guanine. And then last they ask, is this an example of major groove or minor groove interaction due to the due to the number of hydrogen bonds attracted to the guanine pair? This would be a major groove interaction. So with a major groove interaction, a major is the showing of the double helix. It's to describe the double helix structure, and the major shows kind of that outside pairing versus the minor is the inner pairings. And if you're looking for specific bindings, the reason why major groove is shown in this one is simply to do with that OH binding with the rotation of, the guanine binding with the adenine. Because this bond, the way I drew it is slightly crooked, but if these were completely next to each other, these structures are forced to face, I drew it correct here and here, along the 4-carbon and oxygen formation at the pyrene there. But they basically have to fold into each other to allow that nitrogen-hydrogen interaction. And the way that this is attaching up here, this with the interaction of the R groups is on the major groove side. Whereas if it was in the R groups, if it was in the attachment groups down here, this is like the inward interfacing of the bond there. So I guess a good rule of thumb is because these R groups are pointed outwards in three-dimensional space, so if we draw it out like this, let's get be real, you're going to have the nitrogen, you're going to have those phosphate interactions, not phosphate, pyrene interactions on the inside here, and the R groups are facing the outside here, which is where the amino acid is attaching to. So it would be on the major and not the minor, which is in here. And that would be your final answer, is drawing this and then just saying major because of the R group interaction. Don't save. Oh. Opening up everything right now. Nitric oxide is synthesized by the enzyme. Signal transduction pathway. Okay, I'm more focusing on the stuff. If someone wants me to make a different video on the pathway, this is very good information right here that goes into the citric acid cycle that I could cover in a different video. However, let's just go focus on a mechanism problem here. Because I believe there was one. Yes, there we go. Enzyme catalyzed mechanism for hydrolysis reaction. So, sodium, potassium, ATPase. So you know that this is going to be an enzyme because of the ASE. It's activated by phosphorylation of an aspartic acid side chain. So like how I was mentioning earlier, when doing that amino acid problem, we had an glutamic acid. So aspartic acid will be very similar and will have one of those carboxylic acid R group side chains. The enzyme is deactivated by enzyme catalyzed hydrolysis of phosphoratate to produce asparagine. So asparagine is like how it wasn't before, but asparagine is a different type of amino acid, an inorganic phosphate pi. So you know that there's going to be a phosphate group either attached or leaving. Proposed an enzyme catalyzed mechanism for the hydrolysis reaction. You can use enzyme B and enzyme BH for an enzyme base or acid respectively. Cool. So you know that the enzyme is going to be, or sorry, the aspartic acid is going to have an attachment here. So let's first draw this out. So first, let's draw an aspartic acid. Let's give ourselves a little bit more of the page here. NH. Then a methyl group. And aspartic acid, very similar to glutamic acid, has a methyl group, but it only has 2 carbons. So it's 1, 2, and then the rest of that carboxylic acid. So this double bond O comes out here, O minus. And we know that enzyme base is going to want to cyclize and create a phosphorus leaving group here. But I would say the best way to kind of possibly draw this is starting with that enzyme base and knowing that this is going to be a hydrolysis reaction, kind of drawing this out in solution 2. So you think, oh my goodness, so you want it there to be a phosphate group at the end and aspartic acid So you know that the aspartic acid, which is the ASP, sorry, I misspoke. But the ASP will be the aspartic acid and the inorganic phosphate are going to be separated from each other, that they will most likely have a bound side chain together. So you want this to be your final product, which is fine. We can draw it out like this. And then a phosphate group, which should have probably protonation, phosphorus, O minus, and an O group. So if you want this to be your final solution, we should kind of work backwards from this. And you know there's going to be an enzyme with a base and probably a hydrogen attached because of this hydrogen and water in solution. So these are what you're working with. And if this is your final solution, you should first think to attack this problem is, okay, we know that these are going to be attached to each other due to it says phosphorylation of an aspartic acid side chain of an enzyme. So you know that this phosphorus is attached to here somewhere. which is probably one of these oxygens, because phosphorus likes to be a electrophile and nucleophile due to its electron placements. So let's first attach it onto the side chain here. So let's erase this. Alright, let's just start clean here. Don't save. So let's start with redrawing out that aspartate or aspartic acid. With that R group on it. O. And then draw that. So you know it's 1 carbon up. Let's just really emphasize it just so we have more room to work with. Oxygen, O here, and then that phosphorus group. So you know it's going to be O minus, and then double bond O. And they say to show that it's in water and that this aspartic acid and inorganic phosphate get removed from each other. So this is a classic example of nucleophile electrophile attack. And if you do not know what that means, basically, nucleophile is electron rich. They really want to attack things because they have an excess amount of a delta negative that they want to become more neutral. An electrophile is electron poor. It has a positive delta. And the way that things become nucleophiles and electrophiles is just due to their properties. So a oxygen group like this could be a nucleophile, but due to the phosphorus being able to rotate a lot of this double bond to the different oxygens, it's actually a little bit electrophilic because these double bonds like to come down and then rotate around, where the negative is the nucleophilicity is kind of out here with a lot of the negative, which leaves this a little bit positive. And we assume that there's a base in solution. So we say enzyme base would probably attack water in solution to grab one of these protons. And because it's the molarity of water in hydrolysis reactions is really high, and we always assume for biochem that these reactions are in very high concentrations of water because it's in our body. This bond doesn't stay an O minus, rather those electrons immediately attack an electrophile here. But the main issue with this is very nucleophilic. And yeah, this is a little electrophilic, a little electrophilic, but because this R group is very nucleophilic in general. Okay, sorry about that. But basically, because this R group is very nucleophilic, that makes this carboxylic acid carbon kind of electrophilic because of the attached negative R group. So these electrons that are very nucleophilic are going to snake and attack right here. And in one, depends on your intermediate, is going to be create this non-stable reaction where it's, I'm just going to draw R for the aspartic. Yeah, I'll do ASP. ASP, and then methyl it's going to have this intermediate. There's an O minus, an oxygen with a phosphorus group attached to it, and the OH group here. And because this is an intermediate, these electrons really just want to come right back down. But because of that, we need to have a leaving group. And because that OH is very, very, very stable compared to the phosphorus group, the phosphorus group here is actually going to get kicked out. So in one foul swoop, these this bond gets kicked off and put onto this oxygen, and this lone pair probably takes this hydrogen away from this this alcohol group and then gets put onto this oxygen, which then in turn puts you into the spot where you have your aspartic acid, so you have your NH group, which then attacks to this oxygen who just made his double bond, the O group that just got deprotonated here, and then the phosphorus group with an OH, phosphorus, O minus, O minus, and double bond O. And we can't forget about our enzyme and our water here. So the water will just be floating in solution. So there's just a bunch of water in solution. And then the enzyme was protonated, so it'd be enzyme B, and then and not a lone pair, with a hydrogen on it. It'd be positive. So the reason why, just to rerun over this problem, the reason why this problem is so tricky is because it technically has two solutions. Like I said before, this makes this phosphorus very electrophilic too. Or not very, but pretty electrophilic. However, in negative and distribution of charge, because this phosphorus is very negative overall, technically it's a better leaving group than if you were booting out the aspartic acid, because the aspartic acid, even though it has one negative oxygen here, it's pretty stable comparatively to the phosphorus. But if you drew this arrow of this water group attacking this phosphorus, and then you had this intermediate such that this O minus was this guy, and then this oxygen bond was breaking and then attacking the OH that would be attached to this phosphorus, that would also work. It's just that this the phosphorus as a leaving group is a little bit more sense. But there's your solution. Even though, I guess that's drawn wrong. Even though the difficulty of mechanisms is sometimes very apparent, just thinking back to most of these reactions are nucleophile versus electrophile, and how are we going to get to the final stage. Just drawing out everything that you have. So in this question, just saying, hey, I need to have a aspartic acid, I need to have an inorganic phosphate, and they tell me that I can use enzyme, and because it's a hydrolysis reaction, there has to be water. Just put those in each of the solutions, or sorry, put that on the page, and then just kind of working it out from there. And that's basically what this is. Like if you just drew this on the page, you just kind of have to think, okay, these are probably attached to that at some point, and then kind of reverse engineering it from there. And they tell you that it's a phosphorus R group, which is a nice big hint, which is nice. But I think that'll be all for today. if more biochem help needs to be pulled up, I mean, especially with this is a big one with endothelial cells and bloodstream. Um, and there's a lot of good stuff here, which is just a little bit more memorization. I can run through this another day. But for now, that'll be all. Thank you.